Well, welcome to everyone who's here, and thank you, Alejandro, for the introduction. As Ale had said, I've worked with Radiocarbon for about, 25 years now. Originally doing contract archaeology, CRM, as an end user of beta analytic dates. And early on, I was, it was complex. And I didn't really, of course, you read the beta analytic results sheet and it talks about calibration and the Pretoria, sorry, laugh, the Pretoria protocol for calibration. And it talks about the modulation, what is it? The heliomagnetic, geomagnetic modulation of the helio something, which is physics, astrophysics. But I was like, oh my God, that must be important. And it is. And yet once I kept working through and kind of developing the prep techniques and learning how to do stuff on my own, a lot of the what I learned is that a lot of what you do in the first place of selecting samples, understanding the context and the question that you have that you're trying to address makes up probably 80 or 90% of the quality of the radiocarbon date, we'll say. And I won't say measurement necessarily, but at the date, like how meaningful is it? Is it ambiguous as to what the meaning of a radiocarbon date is once you've got it? A lot of that has to do with the choices that the individual makes, the researcher makes at the point of contact with the sample, even identifying what is or is not a sample. That is crucial. And so, I would like to have that kind of carry through in this talk. Really, I'm not going to talk too much about calibration. I'm not going to talk specifically about sampling in a paleoecological context, say of a core, but it will come up because there are certain assumptions I think that paleoecologists, certainly limnologists, make um, that about the depositional processes and things like that will dominate the how meaningful the result is once you have the date. Okay, so the measurement can be fine. If the context is not good or the interpretation of the context is in error or there's some uncertainty, that can have a big effect. So I am going to talk mainly here about sort of the technical side so that you understand technically what goes into this in practice into getting a radiocarbon date. Um, just so that we're kind of opening the black box and kind of ground you. So it's not people making up things every single time. Okay, this is um, important to keep in mind. If you go back through the literature, you will see developments in the technology um, and things like that, but it's coherent. It should be coherent, really. You can go back and find, oh, well, this stuff was really laid down in 1963 or 1977. Those are fundamental, and it's an incremental process of developing and standardizing how we think about the radiocarbon samples. Whoops, I'm getting that. So radiocarbon, as we say, is inherently interdisciplinary. And by nature, it is. Like we tend to think of it either in terms of just the historical sciences, so like archaeology, which is really where all this got its footing, radiocarbon as a technique before AMS, which is accelerator mass spectrometry. Willard Libby, as I'll show in a moment, went to archaeologists primarily and some dendro stuff to validate the technique. But beyond that, I think on the right side of this, we have like hydrology, oceanography, climate science, and a lot of that can be geochemistry or biogeochemistry, depending on what you're doing. And really, it's not so much necessarily about dating, but it's about understanding the radiocarbon content of a sample and understanding climate, well, we'll say carbon cycling first, and then how the movement of carbon can be used to track larger processes, energy flows, and things like that at a ecological level or really a global circulation kind of scale. Okay. And then there are other things within, I guess atmospheric modeling is over on the left. That would be critical to this too. And then other kind of applied things like in forensics, which we're doing a little bit of now, of using radiocarbon dating to figure out the age of, or age at death, sorry, time of death of individuals. And in art history and conservation, it's kind of forensic often in that you're trying to identify, or you can be trying to identify if there's been conservation done at some later date, if something is authentic to a time period or not. And these require greater and greater levels of understanding of materials and process and the human process of production of things, just as in archaeology, paleontology, paleoecology, the physical processes in nature and culture have to be understood to interpret these things correctly. Okay. As a basic concept, which I just got kind of updated recently at a conference, what are we talking about? So radiocarbon is an isotope of carbon. Okay, C12, and if you go back, Google it if you need to, but C12 is the um, most common isotope or form of carbon that we have, C12. There's a stable isotope, and again, if we think isotope has the same number of protons and then a differing number of neutrons. The number of protons is what makes an element chemically behave as that element, okay? When you have a stable, or either if you have an isotope of, say, carbon, it's got extra neutrons and then extra mass, where a proton and a neutron have a mass, atomic mass of 1. Carbon has 6 protons and normally 6 neutrons, so its mass is 12. Okay, so we're talking C12, that's what we mean. Okay, the common abundant form of carbon. Now, radiocarbon is a name for a synonym for C14. Okay, not some isotopes like deuterium, for example, isotope of hydrogen, have their own name. It's not really official, but that's what is meant. When we say radiocarbon, strictly speaking, we're not talking about a method, we're talking about an isotope, C14. Okay. But how do we get it, right? It's radioactive, so it decays. So in theory, if we started with 100%, 4 billion years ago, we should have none in the atmosphere and none in the biosphere at all. It is created when cosmic rays bombard N14, so 7 protons, 7 neutrons in the upper atmosphere primarily. And it basically blows out one of the neutrons, blows kind of a negative charge off of it, a simplistic way of thinking it. Electron, it's not really. And that neutron, one of them becomes a proton. That then, or sorry, one of the protons becomes a neutron. So your mass stays the same. You go from N14 to C14. Now, on its own, it rapidly oxidizes to form C14O2 or radiocarbon dioxide. Okay. We simplify it here, as Walter Kuchera was reminding us back in Krakow last month or 2 months ago. There's actually a slightly stepped process in this, but it happens quickly enough that we don't really see it. So what we have to worry about or think about is the radiocarbon dioxide, the CO2. That mixes relatively rapidly, certainly on annual scales in each atmosphere, the north and south atmospheres. And it's incorporated into plants, whether those are algae in the ocean or on land and lakes or big plants that we're used to seeing. That is where radiocarbon dioxide comes in gets incorporated into sugars and starches, polysaccharides, etc., sugars in plants. When people and animals eat those plants, wherever they are, where they eat other animals or other people, you know, that's how radiocarbon gets incorporated into our tissues. Okay, plants are the direct link to the CO2 in the atmosphere, and then every other part of our reservoir in each of us comes from eating, not from respiring. So keep that in mind. Um, as we note here on the right, some of the CO2, radiocarbon dioxide, is absorbed into the oceans, and that cycles under the surface and is kind of removed from contact with the atmosphere. There you get radiocarbon content out of equilibrium with the atmosphere. We're not going to talk at all really about that, but there are some similarities to other reservoirs, geologic reservoirs that could affect radiocarbon dating in lakes, for example, but I'm not going to dwell on that. So then after the organism dies, the radiocarbon content is no longer in constant exchange with the atmosphere because they're dead. You know, they're not eating because they're dead. And therefore, the radiocarbon content they have at death is the most that they will have, and then it decays after that. By measuring the proportion of C14 to C12, we can then use that to determine the age at death. Okay. Now, I like to go back to Libby's curve of the knowns, and this is from his 1960 Nobel lecture. Wilfrid Libby was a scientist involved in the Manhattan Project. I don't think he shows up in the Oppenheimer film, but he was one of those guys. Okay, and anyway, during developing the nuclear bomb, or sorry, the atomic bomb, they knew of radiocarbon's existence because it was kind of a byproduct of all this other stuff they were doing with reactors. Like you would just have this stuff all over the place. And the thing is, they didn't know what the half life was. But he speculated if the half life is not too quick, meaning like some things decay in nanoseconds, or very long, like say uranium or some of these other things, then because carbon is in all living things, potentially you could use that as a method of dating the age of, of a sample if it has carbon in it, which carbon is everywhere. Right? This would be cool. And so what he did initially, as you can see on this curve of knowns, what most of this is are archaeological. And in fact, everything from like about 3,000, 2.5 back on this, if we look at the historical age, a lot of that is from Egypt. So to go that far back, but have known ages, they were relying. He actually went to these conferences of archaeologists and Egyptologists and classicists and was asking them for, do you have the wood of this coffin from this pyramid that you know what the age should be? Because I want to do this technique. And from his own writing and others, most people didn't really understand what he was talking about or why he wanted these samples, but they helped him figure out what is the actual radiocarbon, the half-life of radiocarbon, which in his first iteration, he had about 5730 years, and then switched it up to 5568, which is what we're stuck with, the Libby half-life, even though shortly after that, he recalculated it to about, again, 5730. Anyhow, I point this out because you've got tree rings, you got some dendro stuff up on the left. Everything else is basically from the classicist or the Egyptologist to help verify the method. So the dendro people, of course, love to say how important they are to radiocarbon, but actually the classicists are also deserve a lot of credit fundamentally. Okay, now again, trying to explain or give people a sense of what actually goes into it. Once you've taken your sample, this is kind of a flow chart here. Once you have a sample, whether it's in the archaeological context or from a lake core or some other context, ecologic or paleoeco context, you have to make the selections of what is going to be a useful sample and what is not. Now, your choices mainly, I think, depend on context, and we can ask about that later. But there are some technical bits that are kind of important, meaning ideally, depending on like if you've got a varved lake, we'll say, okay, and you think that you have varves, and so those should be annual increments. If you're doing radiocarbon dating of macrobotanical or whatever in those, ideally you want those to be single year samples as well. So seeds and leaves grow for 1 year. They're not averaging radiocarbon content over time. Bone in archaeological contexts or others often is only the lifetime of an animal. Now, if it's a small animal like a rodent, typically you're only averaging maybe 3 to 5 years in the collagen of radiocarbon content. So you try to, where you can, make choices to limit the amount of time averaging in your sample, but you do the best that you can with the samples that present themselves in reality. I also, not to go through everything in detail here, but iterative sampling is important. You want to, first figure out in your lake core what is the oldest part of it. When the youngest part is because it's the top and you just sampled it. You look for lithologic changes and maybe you do some initial few dates just to frame the time depth. And then you go in after you've got that to try to tighten up the chronology where you have.
I think Brendan, like the communication, we can't hear you. Okay.
It was good until just a moment ago, and now we still, yeah, still can't hear you even after you muted and then unmuted.
So I guess he's gonna try to rejoin.
Yeah,
Okay.
that makes sense.
Because it's so just let's wait a few minutes and see if we can make it work.
Yeah, I'm sure he'll be back in just a second.
Uh,
Oh, I just heard you. As your image disappeared, your voice started.
can you
Yeah.
hear me now? Am I back?
Yeah.
Okay,
Yeah.
so I was going to turn off the video. This computer is fighting for its life. All
All
right,
right.
so let me now get back to that. And then, whoops, see if this can do it. Okay, where did you lose me?
The
Or,
importance of iterative sampling, I think, is what you're talking about.
okay,
Yep.
good. All right, that's fine. Okay, so, so technically speaking, what we're dealing with is when we do pre-treatment, you're trying to remove carbon that is not the autochthonous carbon or the endogenous carbon from a sample. And usually what you're doing is first, the most common contamination would be carbonates, either in soil or secondary carbonates in geologic carbonates in lakes and things like that. Always you're going to be hitting that with some kind of an acid. Typically it's hydrochloric and it's fairly dilute, but enough to burn off carbonates, which can be contemporary, but often are geologic. Um, then for wood, charcoal, plant material, pollen, um, usually you're doing a humate extraction. So you're using a base to extract the base soluble organic matter, which can be of any radiocarbon age. This is, or people like to extract the humates or the soil organic matter from sediments and then date those. So there, either you're trying to remove the contamination or you think that that is not contamination in a lake sediment, and then you isolate that. Whatever the chemical processes you do are to isolate the original radiocarbon reservoir in the sample. That's what you want, okay? And with bone, we won't go into that, but there's similar methods. Essentially, you're trying to get to a purified version of a sample. We turn that into CO2, either by acid hydrolysis for shell or burning it, essentially, which I'll show you, to create CO2. It's very simple. Sealed tube combustion is quite common, and graphitization then is critical after that. That has a lot to do with backgrounds, but that is a conversion of the gas CO2 into a solid form. There are gas inlet ion sources on accelerators now, but still the bulk of everything is done on solid, which especially for smaller mass samples that are not individual amino acids or something like that. And then finally, you make the AMS measurement where you're actually measuring the amount directly of each of the three isotopes, C12, C13, and C14, usually nowadays on an accelerator of whatever version. So to go over quickly, as I just said, these, and you can, come back to this video if you want, but this acid-base acid, ABA, or sometimes AAA, meaning acid alkali, is a standard pre-treatment. And this goes back, I would say, at least to the early 60s. And certainly Libby, Taylor and Libby and Berger, I think, had a paper in 67 that, shows this, a version of this. This is pretty much a standard type thing. Some people might use potassium hydroxide, but essentially this is what you're doing almost all the time for standard samples. Okay, so you can see in the sense it's not very difficult to do this. You're not with a lot of harsh chemicals. You're doing things on heater blocks, as I'll show you. And it's actually, pretty standard. We do this a lot with students because it gives them some hands-on experience. As you can see, this is when I was a grad student back at Oregon. This is Carly, who was doing ABA, and I was training her on that. So we have heater blocks on the left, pipettes for pulling out the supernatant as you go along, trying to keep things clean. And it's very simple. Nowadays we probably have this a little bit more cleaned up or whatever, but in the end it's a very simple process if you have some basic kind of safety lab chemistry type things going. Well, again, what you're doing is the main part is repeated base washes to extract mainly what we think of as humates or humic acid, fulvic acid to some extent as well. So, and this would be an example of successive base washes on, I don't remember what this was. I think it's wood that we have, probably our background, Pleistocene wood from British Columbia. So these are after you've done each, 6 milliliters of sodium hydroxide. Your first base wash, you can see it's kind of brownish. It's got some color to it. Some of that is the original resins of the wood, which is not a problem. But what we're trying to get out is all the soil dirt, which is much younger, typically, than the wood itself. We want the polysaccharides, the cellulose, ideally, the fat cellulose, not perfect. Second base wash, there's still some coloration to it. Third base wash, it's clean. Now, this is a relatively clean sample to start with. For peats and things like that, it much dirtier. But what we're trying to do after the third base wash, it's like you've gone to excess. There should be no real contamination or, that we can think of. And that's the simple thing. So I'm showing you how simple it is just so that, you don't get too wrapped up in this process. Though, if you give up, say if it is really dirty and you don't do something more complex, there can be a chance of some contamination remaining. That will tend to be younger. So it's organic stuff seeping down from above in most cases where that would be an issue. We finish with a base or an acid wash, HCl, because, and this comes from a very bad grad student at Oregon who eventually redeemed himself, has his own prep lab. But what we see here is in the base washes, because it can absorb CO2 from the contemporary atmosphere. Okay. This is why, and if it dries in this aqueous solution, on the outside of these samples, you'll get this white crusty stuff, which is bicarbonate, sodium bicarbonate, which we know is baking soda. And that CO2 comes from the contemporary atmosphere. Now, if you don't hit that with acid, if you do, it will burn it off and bubble away and you clean it up. If it's inside, or let's say if you handle this while you're trying to pack your sample and you get that modern bicarbonate ion into your sample, you will be dosing it with basically 100% modern carbon. Very small amounts of that contamination can have a big effect on your samples, especially when they're relatively old. If you're in the Pleistocene and you add modern, you will get big shifts. So this is why we do the A at the end of ABA. It's to get rid of any secondary carbonates that could have formed by the process. Once we have our samples dried and clean and happy, then we put them into, this is what we do. There are automated ways to do this, but for batch processing, we'll put them in quartz tubes, clear fused quartz, which can handle high temperatures when we put it in a furnace. And we put in copper oxide powder, and that, because it's going to be under vacuum, there's no oxygen, we add copper oxide, which will reduce and then give off oxygen to allow combustion to happen. We add silver wire. Some people use silver powder, same thing, which grabs chlorides and sulfur that are byproducts of combustion or still in the sample and prevent them from either contaminating during graphitization or etching through the glass and destroying the sample. These are typically sealed under vacuum with a torch and then combusted, typically 900 C for 3 hours, depending. Sometimes we do 800 on salty samples or soil, bulk soil. But this, when you read the methods section in a paper where it says samples were sealed under vacuum or sealed tube combustion with copper oxide and silver wire, this is what it is basically talking about. And you can see the sample and the silver and the copper in the bottom of these tubes on a vacuum line. Those will get evacuated. This is an alumnus of our lab, Maggie Davis, with a torch, natural gas and oxygen torch, which you need to get to that very high temperature, seal it off under vacuum, and then you're ready to go to the furnace. You bake them overnight, typically, because it takes a while to heat up and then cool down. And then we're graphitizing. So pretty much not every method does this. There's a sealed tube graphitization method, which is with titanium hydride and zinc on an iron powder. UC Irvine does this a lot with air samples as opposed to others. But it's an approach that doesn't need as much of the vacuum lines and stuff like this. But the classic, going back certainly to the early 90s, or sorry, late 80s, we'll say, would be graphite reduction on an iron via hydrogen on an iron powder catalyst. So what each of these does, if you look on the left, or I guess mid-screen, but near those dewars, there's a flexible tube. You put your quartz tube in that, and having scored it, you evacuate the whole line, crack the tube, and then the CO2 passes first, or all the combustion gas passes through a methanol and dry ice slush trap, which freezes out the water vapor. Water is a combustion product. Okay, it's inevitable. You get that out. You then, in the next little dewar, you have liquid nitrogen that freezes the CO2 out of the gas that you have. Anything that cannot be condensed by that is then pumped away on a bypass line, pumped out into the atmosphere. Those are mostly nitrogen compounds for the most part in these samples. We then move the CO2 into each of these reactors. On the right, you put the heater, which are hanging up on above there. Onto each one, you heat it up at 550 for, again, 3 hours. That converts the CO2 as a gas into a solid graphite, so solid carbon on the iron powder. And this is essentially how one of the ways that carbon nanotubes and stuff are made, although these form at more of a micro tube scale than a nanotube scale. But the Bosch reaction is quite old, actually, compared to many other techniques. So not a lot of different ways of doing this. Again, there are systems now that automate this, that instead of doing 12 at a time, you can do 7. You have less control. I like our rig, I'm biased. Now, once we have that, as we pull the reactors off, on the left here in the yellow trays, you can see each one of those is the tube, a little 6mm by 50mm tube with the iron powder that has carbon grown on it, or actually under it. So our sample now is a mix of iron and carbon, as graphite, solid samples. Each of those gets pressed into a target using this little jig on the right and put onto a wheel, which you see on the front left. That is the cathode wheel. That will represent one entire run of an AMS sample. So we'll have standards, primary standards. We may have secondary known age standards, and then backgrounds. Backgrounds get subtracted. The activity of those is subtracted from all the samples. Ideally, what you do have is a process background and process unknowns, meaning the same chemical steps that you use to process your unknowns, you do on a similar material. If it was macrobots, for example, we'd probably be using wood, as opposed to just putting in industrial graphite as a background, or coal. Maybe coal's all right. If you're doing bone, you want to have pleistocene bone as a background. Okay, so we use a mammoth or mastodon that is much older, say 70,000 beyond radiocarbon, to check the process. To me, this is a critical part. Again, in the late Holocene, probably it doesn't make that much difference, but with any time depth, ideally you want to know what the process background is, not simply a machine background or kind of an idealized background on something very clean. So that's something you can check on with the labs you're working with and just get a sense of how they approach that stuff, because some reviewer may ask you about it. Now, on to the accelerator itself. This is our AMS, the accelerator mass spectrometer. The mass spectrometry part means we're separating ions and ionized molecules and ions by mass. And typically, the most common way of separating things by mass is with magnets, whether you have a lot of acceleration or not. So an IRMS for stable isotopes typically is using a magnet or an or both, and electrostatic stirrers to separate your stable isotopes. For C14, you need much better separation and hence acceleration. You need, because the content, radiocarbon content is so low, even in the modern setting, that you need acceleration to separate, get clear separation of 13 and 14, or 14 really on its own. Plus you need suppression, isobar suppression in a sense, whether meaning you're not getting N14 in the sample. Ionization helps deal with that. So that you should only be getting radiocarbon ionized as your measurement. In this case, what we've got is this whole system. The ion source is on the right, which I think the next, yeah. So we have cesium, typically is the way of negatively ionizing samples now. Even in the Mikata systems, you have cesium as the thing to donate electrons and charge things negatively, meaning your carbon, your iron, everything in the sample cathode. That has an electrostatic field created, positive on the extractor. The samples are negative, the housing is negative. What happens is this initial acceleration is negative ions of carbon and everything else get pulled out, and you create a beam, which then travels through the injection side to the injection magnet. In this case, it bounces to individually send a 12 mass beam, a 13 and a 14 mass beam, which are separated by the magnet, but they also have to be biased so that you can get them one at a time sequentially into the accelerator to create a beam. So that's an electromagnet, and the housing is what is biased with electrostatic energy there. The accelerator itself, what we run is a 500 kV accelerator, and this is the compact model. The Mikatas are smaller than this, obviously, but the NEC's system and the high voltage engineering systems, which are more common in Europe, 500 kV is considered compact and a small accelerator. For reference, the top of that tank is probably about 8 feet. So it's not really small, but compared to the giant ones, it is compact. You can put it in a room. Then we have the analyzing magnet. Here, this is a static field, which separates the accelerated beam in its parts, sequentially coming through, into 12, 13, and 14. So now we analyze, meaning we measure the content of each of those. Two of them, these little, if you look at the tube thing, there's two little circular bits here on the left. Those are the housings for the Faraday cups. So the 12 beam and the 13 beam are aimed coming out of the magnet to hit these two Faraday cups. When each ion hits a Faraday cup, it generates a current. The current is then integrated and converted essentially into an amount of 12 or 13 in the sample. And that's where they end up. That's their fate. Now, C14 goes down the midline into an ESA, electrostatics spherical analyzer. This discriminates both by mass, but by the mass charge ratio and the energy. So if you had 14 mass molecules like C13H or C12H2 that had reformed or made it through the accelerator, they would have low energy enough that the electrostatic spherical analyzer would pull them out of the line before they hit the detector, right? there at the end, little teeny tiny guy over here, solid state detector. That counts individual ions hitting. Now the ratio, there's like 1/4 in modern background, 1/4 the amount of C14 versus C12. So you're counting individual strikes of, or incidences of C14 in this detector. The multi-Faraday cups are getting a much larger amount, a quadrillion times as much. So you have different detectors for that, but both are used then to quantify the amount of 12, 13, and 14 to get your date. And, all right, oops. So this would be the ion source. I'm not going to dwell on this, but the cathode wheel goes in here. So that would be your whole round of standards, unknowns, and backgrounds. We can run about 30 unknowns if they're all the same material per run. That takes about 22 hours. This is the charging system itself. This is inside the tank. This will be a little obscure, but in the middle of this, down the middle, is a beam line, which is under vacuum. This chain basically picks up charge from the charging system. Each of these little bits on the chain is a pellet that carries charge and that creates the up to 500 kilovolt terminal voltage, which is positively charged. So your negative ions coming out of the system are accelerated towards that point. They get stripped of electrons and become positive when they hit the terminal, pass the terminal, and then get another 500 kV of acceleration after that. Now, an AMS or any accelerator or any, even the solid state liquid scintillation stuff, does not measure the age. Okay, so what we get are the concentrations of C14 and C12. And with that, we have a stat, or statistic, I guess. D, big D, C14, it's the ratio of 14 to 12 with respect to a standard. So the standard, typically we use OX2, oxalic acid 2, which has a known concentration of radiocarbon. So everything is normalized to that concentration so that we know what we can figure out the age. To figure out the age, which is T here, we're doing a natural log of 1 plus the DC14 divided by 1,000 because it's in per mil. Convert that, do the natural log, and then multiply it by negative 8,033. That value, 8,033, is factored from the decay constant, and in this case is the Libby half-life, not the true half-life. If you're doing the delta C14, then that number, if I remember correctly, is 8,267. Okay. That will come up if you are doing things in atmospheric science, if you're doing soil cycling. Either they'll use F C14 or classically delta C14, which is not the same as D C14, but it has that different factor. Anyway, most of the time, and you can do this in Excel, if you get a result spreadsheet that has DC14 on it, you can put in, create a little formula and get the natural log of that in this form, and then get the radiocarbon age. Okay, it's a good exercise because it helps you understand the meaning of some of those terms and what we're talking about, how it is all connected from the isotope concentration to the age. And this is all in Stiver and Pollock 1977, which everyone should read because that is the standard method of getting what we're talking about. Conventional age. So Stiver and Pollock 77 lays out a bunch of conventions, or kind of compiles ones that had evolved and made recommendations. So that in 77 so that people could get on the same page and agree to how they were going to report data. That's what it's all about. Discussion, reporting radiocarbon data. That is the name of the paper. Conventional radiocarbon ages. Okay, this is important for everyone to know. Conventional radiocarbon age, by definition, by convention, which is why it's called conventional, they're corrected for fractionation by normalizing to a delta C13 value of -25. Okay. This is important because this is correcting for fractionation in nature. If you have C4 plant, C3 plant, that fractionation, but it also accounts for fractionation during graphitization, which can happen, and on the AMS itself. So you lose our efficiency, ionization efficiency is about 20% on our machine. Typically 10% is kind of a standard amount. What that means is you're losing a lot of sample, and a lot of that is mass dependent fractionation. So we use the delta C13 on the AMS, the high energy side, to account for that fractionation and loss. Okay, so this is important. If you go back to older data, I'll just jump ahead through this, right? If you go to older data, if you're looking at older lake cores, maybe something that hasn't been sampled since the 70s or 80s, you can look at some of that. It won't be clear whether it's a conventional corrected age or not, but it matters because, every 1 per mil difference in delta C13 is about 16 radiocarbon years. And if you look at, unconventional, if you had a C4 plant, it's 2000, you're looking at about, more than, it's 12% difference in age. And this can matter a lot, regardless. If you go to old data, if it's unclear whether it was measured, delta C13 or estimated, you want to keep that in mind as whether when you come back to this, if you recore a lake, for example, you will have a conventional age typically now, but if you're trying to compare it to an older sample, that may be something to take into account because it wasn't always well documented before certainly 1980, we'll say. This as estimated delta C13 corrections. This is 1977. This is in Stiver and Pollock. And this is a list of different materials and kind of ranges that empirically people had observed, right, at the time in using IRMS. And you can see the difference between kind of your 0, which would be like the ocean primarily, something about that plus or minus, and then -25, which is kind of your standard, given depending where you are, C3 plant. And the offsets as they calculate them are up there on the left. And people in the past sometimes would simply use those offsets. I know archaeologists back they would subtract 430, say your upper left-hand corner, from a shell measured age or something. Yeah, measured age, not conventional. And instead of doing a delta C13 correction, and they would also deal with the local reservoir effect, which we're not going to talk about. But it can be very confusing, even in relatively recent literature, say the 90s, if you're looking at marine stuff, how some of these things would be applied. People thinking, oh, I'm using the delta C13 correction, and that takes care of my marine reservoir. And it's like, that's not how it works. So you should not use this table for anything other than to help understand choices that people were making back in the past. Okay, so nowadays everything is typically measured on the machine to give you your conventional age. If you have something where it's presented as a measured age, that's typically means it's normalized to the primary standard, OX2, but there has not been a delta C13 correction applied to it. Beta analytic, for example, I believe they used to report both. When I was starting out, I didn't know the difference. It made no sense to me. Nobody could explain it to me. And I know a couple of instances where I just completely whiffed and put the wrong thing down because I was like, well, certainly the measured age would be what you want, not like conventional age. Like, I'm not a conventional person. I'm an awesome person. Nothing I do is conventional. So clearly, as an empiricist, I want the measured age, right? Anyway, I bring this up because often you'll be coming back through older literature, and it does make a difference in terms of understanding what you've got and how to reuse or reanalyze old data, especially in creating new age models before you go on, a campaign of coring a lake. Clearly, you want to go back and at least get it on the new calibration curves, which we'll talk about, I believe. Before you invest a lot of energy, you need to see, like, what am I dealing with? I've worked on sample on a lake, cored in the 80s by Paul Collin, though, not a slouch. That guy pretty much invented whole parts of modern paleoecology in lakes anyway. But he had a completely whack age depth model. And if we had gone at this on St. Paul Island, in the Bering Sea, looking at mammoth extinctions, and what we ended up with was a completely different model that made more sense. But you have to take that literature and understand it. The lithology is still important. That will not change much. But how you interpret that age depth model matters, and you need to redo calibrations at least. Okay, so which brings us again to calibration. So the initial assumptions that we had from Libby, which he lays out, a number of them were immediately understood to not be correct. So we needed there to be a constant rate of C14 production in the upper atmosphere. That doesn't hold true. And then there's an assumption of equilibrium or lack of partitioning between reservoirs. So we know both of those simplifying assumptions are not correct. And then the question was, well, how do we account for those? So calibration, by measuring primarily tree rings, which are dendrodated, to get continuous records. And now we're moving into from decadal chunks that are averaged to 5 years to single year records, even some that are local. That accounts for these fluctuations in radiocarbon production through time, and also changes in ocean circulation that can spew up old carbon or take in excess modern carbon that changes through time. This is what the Dendro people, amongst other things, have the main contribution, I think, that they've made to radiocarbon. I'll sit on that for a moment. You can again go check this out if you want. As an example of what our tree ring records look like, this is from IntCal 13. Two different periods, and you see the curves, but each of the data sets here is from a different lab. Yes, from different labs of different sections of tree rings. And some of these are quite old. The Seattle tree rings mentioned there on the left are from the 80s, I believe. So that would be Minzy Stiver and his crowd initially. And Belfast would be like Mike Bailey, like the really old school stuff. Bernd Kromer would be involved in the Heidelberg stuff. So way back, and it's still part of the curve. Okay. They've added more to it as we go. And you see these wiggles and fluctuations. Okay. So this is what we're dealing with. That is what the radiocarbon activity at any given time on the bottom, calibrated BP. It's a parent age, conventional radiocarbon age. Today is on the left. So you see they're quite big offsets as you go further back in time, regardless of which half-life you use. Okay, so this is why you need calibration. It's not one-to-one. In passing, and I'm not going to get hung up on this, you also see a very short term on the scale of 1 year or a couple years of spikes in radiocarbon content recorded in single tree rings, which is known as Miyake events after, what is her name? Fusa Miyake. And this has been really for the last 10 years a huge effort to replicate these, identify more of these events, explain what their sources are, whether they're solar events or cosmic background galactic radiation events, or both, or combos, different things at different times. Typically, this will not matter too much for someone coring a lake, but just know these things now, as we get more precision, very short term events are now more visible than they ever were. As an example of calibration, this will actually run. Oh, yeah. So this is from Martin Blau, who you guys should know because, Bacon you wouldn't have without Martin Blau. He's a very cool guy. I've had great opportunities to run into him and hang out a couple different times. He has this animation on his website. So what you're looking at is how our normal distribution here, the measured age, with one standard deviation there in red. So if you rotate this counterclockwise 90 degrees, what you have is the mean, so that'd be radiocarbon age, 2450, and its standard deviation of 50. When you plot that against the radiocarbon curve, you have these plateaus, for example, but when you have the highest density in the measured age, so right there, you get a higher peak translated through that curve. Now, if you have a lower peak, like we're right about, that's high again, low, high, and then it's going to be low, low, low. You're basically multiplying the density of the measurement probability versus the curve probability. That's what a calibrated age at this time using, I think, in Cal 13 will give you. This calibration is the likelihood of the actual age. This is what, for a single sample, you need to think in terms of. So the density, probability density that correlates or is analogous to the 95.4% to sigma, to standard deviation range, is calculated from the density of this kind of weird non-normal calibrated curve, which we'll see here. The way that works is we take each individual bit of time, say 1 year, 5 year, 10-year increment of calibrated time. Imagine that it's a histogram. Okay, so it's a bunch of columns stacked up. We'll pick the highest likelihood or the highest density increment, which is going to be around like right where this hits on the top, right? Around 2490, something like that. And then we keep adding these densities as we include them from highest to lowest. And when we pass 95.4, that is when you have the kind of 2 standard deviation credible interval. This is how a single calibrated range is developed, but it's also what is used in something like Bacon. It works, he does it somewhat differently, but it is those densities that you are looking at to try to match in a sequence. And I'm not going to talk about Bacon because I believe you probably will have whole other things about that. But I will finish on this, which will be relevant for many people in South America and Africa continentally, is with the calibration curves. I'm talking about IntCal, which is the Northern Hemisphere curve, SHCal, and there are other versions. There's a Hulu thing, whatever. Those calibration curves account for the fact that in general, you have offsets depending on time, but in recent past, about 20 to 80, we'll say, radiocarbon years difference between the northern hemisphere and the southern hemisphere radiocarbon content. Um, and that's basically defined as the northern and southern summer extent of air masses where they show up on the ground. So it's not the geographic hemisphere. It is where these air masses originate that is relevant. So if you look at the kind of yellow where you have the January ITCZ, the intertropical convergence zone, meaning the convergence between the two air mass bodies, right? It dips down basically because of the annual monsoonal weather patterns, that where those two masses meet drifts south during the growing season in South America and in, say, Central Africa or sub-Saharan, I guess, well, Central Africa is not exactly correct, but where you have the monsoonal influence from the Indian Ocean coming in, so from the northeast, we'll say. And you can see that where those masses are, that is the northern hemisphere air mass. Now, there is mixing, of course, between north and south. But the argument has been that during the growing season, right? So if you're measuring macrobotanical stuff, the growing season is when that carbon gets fixed. Okay, the plants are growing. They are taking CO2 and growing cellulose and growing fruits and whatever, right? If that is northern hemisphere, because you happen to be in the Amazonian basin, for example, or in the Great Lakes region, we'll say, if that is northern hemisphere air mass when stuff is growing, even if you're in the southern geographic hemisphere, you should be calibrating with the northern hemisphere curve, INTCAL. Arguably, and people have their own takes on this, in my experience, if it's unclear what you should be doing, or you can't make a strong argument one way or the other, what you can do is just assume various mixes. So let's say, okay, in Oxcal or whatever, probably in bacon, you can do this too. Mix the northern and southern hemisphere curves in your calibrations and your age models in different proportions. Say 100% north, 100% south, 50% of each, maybe 25-75 and 75-25. One, you will find out what difference does that actually make. And I'm saying you do this like on your own, not necessarily in the paper if you're writing a paper, but you do it to figure out as a sensitivity test. Like, well, okay, if my assumption is way wrong, how big of an effect is it going to have on my age depth model, for example? It may not have much, or you've accounted for that error and you can say, well, in reality, what we're putting in the body of the paper is a 50-50 uniform random distribution. If it was the north, you might expect the whole age model to shift 20 years younger, or sorry, the opposite. If it's all south, then it should be younger, but it's only by a couple of decades. Once once you've characterized what the uncertainty is and present it, then people can take your original data and do whatever else they want with it. But with this, rather than walking into, say, a reviewer's trap, because it's a very obvious kind of a objection or thing to raise, if you don't already have that, say, in the supplemental material, in my experience, it's an easy thing for people that really don't even have anything particularly constructive or insightful to say as a reviewer. They're like, well, I have a reason to think that, on this side of La Paz, like if I'm in the south, western neighborhood, that is the southern hemisphere. But, if I'm over here, like in central La Paz, that's actually northern hemisphere. And like where my grandma lives, it's like right in the middle, and you're like, Okay, that's just not constructive. But if you've already presented the analysis and you know for yourself, like, yeah, let's, the error in our age depth model may be already larger. The uncertainties may already be larger. But you do want to look at this because it will, at least for yourself, do a couple different models, and I think it will help you understand the magnitude of the problem. Okay. You can deal with this in terms of age depth modeling, and you will realize that a sample that is just a bad sample, wrong attribution of depth will have far more impact on your age depth model than whether you pick north or south, right? That's what you want to focus on, you know. But to me, is getting good samples that are credible to start with. Because you can't undo that. You can't, unanalyze and reanalyze a sample from the real data. You can go and sample again, um, but those will have a bigger impact on whatever your chronology is in a lake or land or anything. Always having that straight up. And I think I'm going to leave it at that, I think, because I had some other stuff with marine from another talk, and I don't think that we need that for this. We're going a little long. Um, so maybe we'll open it up to questions if you guys have any.
Thank you very much, Brendan. That was very interesting. I don't know, we have time for probably a couple of questions. If anyone either wants to just speak or write down your question, please do. Hey, okay, someone is raising his hand or hand.
It's me.
Oh,
Sarah.
sorry, guys.
To kick stuff off while people are thinking about questions, I guess I had one that's like maybe kind of a short one, Brendan, and I was curious about, you mentioned the micatus, and I was actually going to ask you about that if there was time.
Yeah.
Have you had a chance to use one? Could you just maybe briefly talk about what it is and what the advantages are?
I have not used one. I have been to, well, okay, whatever. I'm not gonna, people have used them. I mean, they're spreading all over the place now. And practically speaking, the advantages would be, so compared to what I put back up here, if you can probably fit the classic Micatus, say from the left-hand side here to kind of just short of the analyzing magnet. So the footprint of it, and then bring that out a little bit, right? So the footprint of them is smaller. There are basically no moving parts in the accelerator part. Meaning, so like the chain and all this other stuff in the charging system is not there. It's a static, I think they run at 200 kV or 220, something like that. But it's just a static terminal, not a chain, not all this other stuff with motors and things that can break. It doesn't use SF6 as an insulator because at that voltage, you can use helium, and people prefer that because SF6 is a greenhouse gas, I guess. It's compact. The older systems that were actually made at ETH Zurich, people love those. The few people that have the first 5 or 10, maybe. The ones that are now made by Ion Plus that people are buying seem to have a lot more difficulties in terms of the physics and the space charges within them. They've, anyway, with this machine that I'm showing you, if one is inclined or foolish and inclined enough, you can actually go in and fix this yourself. Okay, there are a lot of things that have to be maintained, but you can do it on your own.
Yeah.
Ion Plus is not like that. The advantages claimed originally would be that you could have small sample sizes with good background. A lot of it is automated. It is set up theoretically that you can do gas injections. It's a gas ion source is the same. So you could be running, do combustion in an EA, route some of that gas to an IRMS, and then the same remainder of that same gas goes into the ion source. So you skip graphitization, that whole step. You then have a trade-off because you're getting less sample, you have less ionization efficiency with a gas because it's CO2 going in and you've got to rip off the oxygen, etc. So your precision often is going to suffer a little bit with that. So it's like you're kind of a trade-off of the automation, and like EA measurements on the same gas is a cool thing. If you can make all three of those components communicate, which has been a huge problem, and then the backgrounds are not as good, or it's not, you can't quite, people are having trouble getting the backgrounds quite good. Like it's just hard to optimize those things. Um, so I mean, and I'm not just ragging on Makatas because, but there was last fall or the year, whatever, a year and a half ago, at Woods Hole, the Makatas people, the new Makatas people mainly, and IM Plus hosted at Woods Hole, No Sam's, along with Irvine and Yale, Brad and them, um, a workshop to talk about Makatas and create these working groups. Because, like, physicists were like, I don't understand why the fractionation of the delta C13 goes the opposite way of how it should, because physics doesn't work like that. And it was kind of a litany. It was a 2-day thing, the public part, and it was just kind of a litany of people's problems or challenges, if you want to be nice about it, with those machines. So, it's an early phase kind of with the manufacturer. Um, and I think, as I've been told by people who work with them, getting all three, getting the efficiency, getting a good background and precision, and routine operation, you don't get all of those in small samples. You so far it's been hard for people to get all three at once.
Okay, thanks. That makes sense.
Thank you. Does anyone has another question?
There's a question from Chiamaka in the chat, Alejandra.
Okay. So Chamaka says, thank you very much, Brendan. I missed this detail. Can you please repeat which is more appropriate to calibrate radiocarbon dates from sub-Saharan Africa, INCAL or OSCAL, and why?
Well, as I said, so I'm trying to remember which paper it was, but it was, I believe, with Mary Prendergast. We were kind of going over this many years ago, several years ago, I should say, and we're starting some work again. That what I suggested to her, and then she actually implemented it. I believe it was her. And other things we've done with the Reich crew, where we had stuff from Malawi, Kenya, Tanzania. I don't think Zimbabwe, but I want to think there maybe Uganda. Anyway, East Africa, Sub-Saharan East Africa, Rift Valley, and like that. Ultimately, what they had presented, I think she did a 50-50 uniform mix of the North and the South, and using Oxcal, because that was for individual samples that we were doing. And what was presented, I think, in the main body of the text, this would be in Nature or Science or something. In the main body of the text, we stated we are using, say, a 50-50 mixture, uniformly going random in Oxcal. And then in the supplemental, I did a breakdown, or asked her to, of what if it was 100% North, what if it was 100% South, meaning IntCal or SHCal, And I think we might have broken it down a little bit more, 25, 75, 75, 25. Put that in the supplemental. Up front in the text was we're going to be presenting in the body our chronology based on, the 50/50 or whatever we did. In the supplemental, all of the outcomes for however many dates, human beings it was, we presented that in a table so people could see what the difference was. And in the end, very little, especially if you're in the middle Holocene, like, does 80 years calibrated matter compared, to the uncertainties already in the curve? No. So that would be my take. You would look at the local literature. So, like, if you're in the Andes or if you're in whatever, you're doing some Tiwanaku stuff or Wari in South America, right? You've got your whatever, Eric Marshes of the world, or people who have said this is how you have to do it. Okay, so you do need to check on what the expectations of your audience is going to be, or what the kind of the state of the art or state of thinking is in the literature that you are entering, or that the context that you're in, to see what is normal or what is expected of your calibration. Having said that, that's why I say if you did different iterations, even to start with one radiocarbon date you make up, okay, 2000, calibrate it with both curves, figure out how to mix them, and then just look at the calibrated ranges at 2 sigma. So you can impress upon yourself, like, well, this doesn't really matter compared to did I excavate this place correctly, right? Like that would be a more important question. But you can easily characterize what the offsets might be. So I recommend that.
All right, thank you very much. Well, thank you everyone for sticking around. So just a couple announcement. We are gonna have another talk, online talk, in about the end of October, by Lorena Becerra. She's gonna give a tutorial on Oxcal. So we're gonna be mailing you all if you're interested to attend. And then, yeah, thank you very much, Brendan, again for your time. Like this was a really great and informative talk.
Great. Well, happy to be here. Thank you.
Yeah, thanks, Brendan.
All right. Bye, everyone.
Bye.